Welcome to day 5 of differential equations. Today we're going to cover section 2.5 and we're going to continue covering part from the material from the appendix that we'll be using later in the semester. Let's start with a definition. If f of tx, ty is equal to t to the alpha of f of xy for some function f and for some real number alpha, then we say that f is homogeneous of degree alpha. So extending that to a differential equation, m of xy dx plus n of xy dy equals 0 is said to be homogeneous if m and n each are homogeneous of the same degree. So we have a way to determine if a function is homogeneous, and then if these two functions, m and n, are each homogeneous of the same degree, then we have a way to classify this differential equation as homogeneous as well. So before we jump into applying this to a differential equation, let's just look at a function f of xy is x cubed plus y cubed. Let's determine if this is homogeneous, and if so, to what degree. So our test is, according to our definition, we're going to replace x with tx and y with ty and see if we can get back some t to a number times our original function. So f of tx, ty, replacing all instances of x with tx and all instances of y with ty, we get tx cubed plus ty cubed. Properties of exponents turns this into t cubed x cubed plus t cubed y cubed, which is, I can factor a t cubed out of both of those. I get t cubed times the quantity, x cubed plus y cubed. Notably, x cubed plus y cubed was our original function, and so this is t cubed times f of xy. And so we see f of tx ty is indeed equal to t to some alpha times our original function. So this is homogeneous and more than that, it's homogeneous of degree 3. Okay, let's apply this to a differential equation. Say I have x squared plus y squared dx plus x squared minus xy dy, and this equals 0. Let's determine if this is homogeneous, and if it is, to what degree. In this case, m of xy is equal to x squared plus y squared. So m of tx ty is tx squared plus ty squared, which can be written as t squared. I can factor the t squared out, get x squared plus y squared. And so I do indeed get that M is homogeneous of degree 2. That's not enough. I need N to also be homogeneous. N of xy here is x squared minus xy. So N of tx ty is tx quantity squared minus tx ty. Again, I can factor a t squared out of both of those terms, and I'm left with t squared times the quantity x squared minus xy, which is t squared times our original function. So both m and n are homogeneous of degree 2. Since both m and n are each homogeneous and of the same degree, this differential equation is homogeneous. Okay, so legitimate question then is, how does this information help us? Since this is homogeneous, since this differential equation is homogeneous, we are going to make a substitution. Since this is homogeneous, we will let y be equal to some function u times some function x. Let's just suppose that y is some function u times some function x. And we're going to see later on in this semester why this assumption is helpful. Just for now, let's assume it to be the case. If y is equal to ux, then dy, the derivative of y, this is a product rule since both u and x are functions of x, is u dx first times the derivative of the second plus the second times the derivative of the first. So we get that dy then is equivalent to u dx plus x du. Making this substitution into our original differential equation gives us x squared plus not y squared anymore, but ux squared times dx, that didn't change, plus x squared minus x times not y anymore, but ux, and not dy anymore, but u dx plus x du, and all of that equals 0. Let's clean this up a little bit. I get x squared plus u squared x squared dx. That dx also gets distributed to the x squared. Plus, I need to multiply all this out. I get x squared u dx plus x cubed du minus x squared u squared dx minus x squared u times x du, so x cubed u du, and all of that equals 0. And a legitimate thought here might be that we have made this significantly worse than what it started out as. You might be right, but let's continue simplifying. Let's see if anything shakes out of this. I'm going to keep Yeah, let's just simplify. All right, so I have x squared dx plus u squared x squared dx plus x squared u du, no, x squared u dx plus x cubed du minus x squared u squared dx. That's going to take this away. And I've got a minus x cubed u du. So that's going to go away. And all of that equals 0. So let's isolate our du's and dx's. So I get du times, I'm going to keep the du on the left. I'm going to move the dx's to the right. For the du's, I get x cubed times 1 minus u. And for the dx's, moving to the other side means I'm going to pick up a negative. I get x squared times 1 plus u dx. Dividing both sides by 1 plus u and by x cubed gives me 1 minus u over 1 plus u du is equal to negative 1 over x dx. So we started with this differential equation, which was not separable. We made the observation that it was homogeneous. So based on that information, for some unknown reason we'll explore later in the semester, we made the assumption that y was equal to ux. And the consequence of that was the differential dy is equal to u dx plus x du. And when I plugged that back into the original equation, I ended up with a separable differential equation. Now I can integrate both sides here to find out what u is. So we started with x squared plus y squared dx plus x squared minus xy dy equals 0. We made the observation that this is homogeneous because each of the components are homogeneous. Based on that information, we made the substitution y is equal to ux, and that gave us one minus u over 1 plus u du is equal to 1 over x dx, a separable differential equation. Now I will point out, since y is equal to ux, that means that u is equal to y over x. So once I solve this for u, I can find out what u is as a function of x, then plug in y over x for u. And when I do that, I get x plus y squared is equal to cx, some constant, e to the y over x. To integrate this, you probably want to separate this. This is 1 over 1 plus u minus u over 1 plus u, and then you can integrate each of those. Okay, so this is the benefit of being able to classify a differential equation as homogeneous. If a differential equation is homogeneous, then we can make this substitution that y is equal to ux and u is equal to y over x, which will then give us a separable differential equation that we can solve using existing techniques. By observing a property about this differential equation, we were able to make a substitution which gave us a differential equation we could solve. Let's have another definition. We're going to define here is Bernoulli's equation. Bernoulli's equation is a differential equation of the form y dot plus p of x y is equal to some function of x times y to some power n. If y to the n wasn't over here, it wasn't on the right-hand side, then we could use integrating factors to solve this differential equation. But since y to the n is over here, this isn't linear anymore. It's not a linear differential. Well, let's be clear. For if n is 0, we note that this is in fact linear. And since it's linear, we can use integrating factor. If n is 1 even, this is still linear because I get on the right-hand side f of x times y to the first power. I could move that over and end up with y dot plus p minus f y, which is equal to 0, which is linear. And so I can use integrating factor. So in Bernoulli's equation, if n is 0 or 1, it's still linear or can be written so that it is clearly linear, and we can use integrating factor. So the question becomes, well, what if n is 2? Now, if n is 2, we are in the nonlinear scenario and we don't know how to handle this. Thankfully, someone, don't know who, came up with the idea to let u be equal to y to the 1 minus n. So if the equation is of a very specific form, we can make a substitution, which presumably turns it into something we can solve. Notice we had this approach before. If it was homogeneous, then we use the substitution y equals ux. If it's Bernoulli's equation, then we use the substitution u equals y to the 1 minus n. Let's see this at work. Say we have the differential equation xy dot plus y equals x squared. I can rewrite this as y dot plus 1 over x y is equal to x, provided that x is not 0. And technically this is a Bernoulli equation, but in this case, n is equal to 0, because I could write this as y to the 0, but this is linear. Can you just use integrating factor on this? Right, I can let mu be equal to e to the integral of 1 over x dx. Then this is e to the natural log x, which is just equal to x. Multiply everything by x here. I get back the exact same equation I started with, which is notably the derivative of the product xy. And so I can integrate both sides here, get the integral of the derivative of the product, giving me that xy is equal to 1/3 x cubed plus our constant of integration, and y then is 1/3 x squared plus our constant divided by x. We didn't need anything new here. This was already linear, so perhaps not incredibly beneficial. So let's do another example. So let's take the same form, the xy dot plus y is equal to x squared y. This is Bernoulli. It's Bernoulli with n equals 1, but remember I told you that if you just rewrote this, this is linear and thus solvable using integrating factor, letting mu be equal to, we're just taking the moment to rewrite this as y dot equals 1 minus x, no, y dot plus 1 minus x squared over x, y is equal to 0. This p of x is 1 over x minus x, and so we let u be equal to e to the integral of 1 over x minus x dx, which is e to the natural log x minus 1/2 x squared, which is x e to the negative 1/2 x squared. Multiplying everything by that gives us, on the left-hand side, the derivative of x e to the negative 1/2 x squared times y. And on the right-hand side, well, 0 times that stuff is still going to be 0. So integrate both sides. I get x e to the negative 1/2 x squared y is equal to some constant of integration. And solving this for y gives us that y is equal to some constant over x e to the negative 1/2 x squared. Again, we didn't need any new techniques yet. So let's bump it up. Say I have x, y dot, same left-hand side, but on the right-hand side now, I have not x squared, not x squared y, but x squared y squared. Now I've entered the nonlinear case, which means my previous approach probably won't work. This is Bernoulli with n equals 2. Which means that we are going to let u here be equal to y to the 1 minus 2, or y to the negative 1. Now, a consequence of u being equal to y to the negative 1 is that y is equal to u to the negative 1. And another consequence is that dy dx is equal to, using chain rule, dy du times du dx. And the derivative of y with respect to u, if y is equal to u to the 1/2, or sorry, u to the negative 1, then the derivative of y with respect to u is negative 1 over u squared, and we don't really know what du dx is. So let's plug this in. I have x times y dot, but we just said y dot was negative 1 over u squared du dx. plus y, but we just said y was 1 over u. And this is equal to x squared, not times y squared, but times u to the negative 1 squared. So everywhere there was a y, I replaced it. Everywhere there was a dy, I replaced it. Let's clean this up a little bit. I'm going to multiply everything by negative u squared. So I get x du dx minus, I'm multiplying everything by u squared, so I get u. Now the right-hand side here is x squared times 1 over u squared. If I multiply everything by u squared, that just becomes an x squared. And what we observe immediately is that this is a linear differential equation. This is linear in u. So we can say that du dx minus 1 over xu is equal to x. Now we can use an integrating factor. Let u be equal to, I've already used u, let's use mu. Let mu be equal to e to the integral of negative 1 over x dx. E to the negative 1 over x dx is e to the negative natural log x, which is e to the natural log 1 over x, which is just 1 over x. So if I multiply everything here by 1 over x, I get that the derivative with respect to x of 1 over x times not y, but u is equal to 1. This should be a negative x squared and a negative x and a negative 1 because I multiplied everything by negative u squared. All right. So I get that 1 over x times u is equal to, if I integrate both sides here, I get negative x plus our constant of integration. And so u then is multiplying everything by x. I get negative x squared plus cx. But remember, now I have u was equal to y to the negative 1, and y was equal to u to the negative 1. So y then is u to the negative 1, which is negative x squared plus cx to the negative 1 power. Or if you prefer, 1 over cx minus x squared. And we were able to, using this substitution, we were able to turn a differential equation we didn't know how to solve because it's nonlinear into a linear differential equation that we do know how to solve. Okay, I'll give you an example to try on your own. So say we have the differential equation y dot is equal to 2x No, that's not a Bernoulli. All right. Let's try instead. Xy dot plus y is equal to x squared, y squared. And this time, I'm going to stop the recording so that when you come back, you can see how you did. I'll see you in a minute.